Good day everyone, I am Annalyn B. De La Cruz from Beside Math 3A, and today I am going to present my geometric model under Abstract Algebra course or M115. So here's my geometric model. I call it a star box because, as you can see, it is a combination of star and box. Let's see the rotation of this model. Let's start with the front moves. So we have D is equal to do nothing, R rotate 45 degrees clockwise, E rotate 90 degrees clockwise, A rotate 135 degrees clockwise, M rotate 180 degrees clockwise, I rotate 225 degrees clockwise, and rotate 270 clockwise, G rotate 315 clockwise. So here's the rotation for front moves. Next, we have the back moves. First is 1. Flip vertically, 2. Flip horizontally, 3. Flip over right diagonal, 4. Flip over left diagonal, 5. Flip vertical and rotate 45 degrees clockwise, 6. Flip vertical and rotate 135 degrees clockwise, 7. Flip horizontal and rotate 135 clockwise, 8. Flip horizontal and rotate 45 degrees clockwise. So here's the back moves. So let's start. Start D, do nothing, then do nothing, the result is still D. Next we have R star 8. R is rotate 45 degrees. So as you can see, D is our first movement, then we will move it to R, which is 45 degrees. So G is our on top right now. And then 8 stand for flip horizontal and rotate 45 degrees. So as you can see, here is the horizontal. So here's the horizontal. So we will flip it. So 6 is on the top right now. And then we will rotate it to 45 clockwise. So the answer is 5. Next is 2 star R. So we have to flip horizontal. So this is the horizontal. So we will flip it. And then R stand for rotate 45 degrees. So we will rotate it to 45. So the answer is 4. So we have 7 star R. So R stand for flip horizontal and rotate 135 degrees. So we will rotate it first to, we will flip it horizontally. So here's the horizontal, we will flip it here. So here. Then we will rotate it to 135, 45, 90 degrees, and then 135. So our top right now is 2. Then R stand for rotate 45 degrees clockwise. Since this is our top, we will rotate it to 45. So our answer is 1. So here's the full table of result for our geometric model. Now let's identify if it is a group. We can call it a group if it is closed, well-defined, associative, has identity element, and has inverse. Now let's check if it is a group. So let's check if it is closed and well-defined. As you can see, the output is unique and under our set. Therefore, we can say that it is well-defined and closed. Next, let's check if it is associative. So here's the table. If we rotate 180 degrees and interchange the row and column, we should get the same structure of our original table. So here's our table. After inserting and interchanging the row, the resulting elements and the flip table is like on our original table, so therefore we can conclude that it is associative. Let's check if the identity element exists. Our identity element is D because there is an intersection between row and column on the table, and that's D. Next, let's check if the inverse element exists for all. So, as you can see, the inverse of D is D, the inverse of R is G, the inverse of E is N, the inverse of A is I, the inverse of M is M, the inverse of I is A, the inverse of N is E, the inverse of G is R, the inverse of 1 is 1, the inverse of 2 is 2, the inverse of 3 is 3, and so on and so forth. So, inverse element for all exists. So, since our geometric model is closed, well-defined, associative, has inverse, and has identity, therefore we can conclude that the geometric model forms a group structure because it satisfied all the given conditions. That ends my presentation. Thank you for listening.